Okay, let's dive right into this explainer. We're uncovering the hidden realities of modern software supply chains and, crucially, how to protect your codebase from malicious third-party libraries. Look, if you're writing code today, you are standing on the shoulders of giants. But what happens when those giants are compromised, abandoned, or actively working against you? Today, we're going to unpack exactly what you're inviting into your application every single time you install a new package, and, more importantly, how to defend your systems. So here is our agenda for today. We'll be covering the invisible attack surface, the anatomy of malicious code, real-world package disasters, vetting your dependencies, building a defense strategy, and finally, the incident response plan. Section 1. The invisible attack surface. We have got to completely shatter this illusion that your app is just the code you write yourself. Research from the SANS Institute reveals a staggering reality. 80% of codebases contain at least one vulnerable dependency. 80%. Every single library you add expands your attack surface because, and this is key, library code runs with the exact same privileges as your application code. If a third-party library is malicious, it can do absolutely anything your app can do. Read your database? Yep. Access the file system? For sure. Exfiltrate sensitive data over the network? You bet. A vulnerability in any library is, fundamentally, a vulnerability in your app. And that brings us to the terrifying reality of transitive dependencies. These are basically strangers invited into your system by your actual guests. You might explicitly install a framework you know and trust, right? But that framework might pull in dozens of other micro-libraries that you have literally never heard of. Every single one of those transitive libraries is a trust decision you didn't even know you made, and any weak link in that sprawling chain can completely compromise your entire application. Section 2. Anatomy of malicious code. Now, beyond the known vulnerabilities, the standard CVEs your automated scanners usually catch, every single NPM or pip install exposes you to a much broader set of risks. We're talking about intentional backdoors in malicious packages. Then you've got abandoned packages, where there's absolutely zero active maintenance to fix newly discovered flaws. There are also restrictive license risks that could legally dictate how you distribute your own software. And honestly, you can't ignore the operational risks. Think about a vital package depending entirely on one single maintainer. If they burn out, your entire infrastructure is suddenly in jeopardy. One of the most common and frankly sneakiest attack vectors is typosquatting. Imagine it's late, you're a tired developer, and you make a simple typo during installation. Instead of typing requests with an S, you accidentally type requests. Your package manager doesn't know any better. It just dutifully goes out and fetches a payload built by an attacker, injecting malware straight into your environment, all because of one missing keystroke. Attackers are also going to use dependency confusion. This is where they exploit exactly how package managers resolve names. Let's say your company uses an internal tool called, internal utils. An attacker can just publish a malicious package with that exact same name on the public registry. If your build system checks the public registry first, bam. It gets tricked into pulling down the attacker's code. And then, there is protestware. This is a wild operational risk where a maintainer intentionally adds destructive, politically motivated behavior to their own project, sabotaging the very code they built. Section 3. Real-world package disasters. Let's look at an escalating true crime history of the codebase, because this isn't just theoretical. Back in 2018, the event stream package, which had 2 million weekly downloads, by the way, was handed over to a new maintainer who quietly added a dependency specifically designed to steal cryptocurrency from Bitcoin wallets. Fast forward to 2021, the UA parser.js account was compromised to install crypto miners. And then in 2022, we saw the rise of that protestware we just talked about. The maintainer of colors.js and figure.js intentionally broke their own packages, which had millions of downloads. That same year, Node IPC was modified by its author to actively delete files on systems with Russian or Belarusian IP addresses. These were incredibly widely trusted tools. Section 4. Vetting your dependencies. So you really have to ask yourself this foundational question. Do you actually need this dependency at all? Think back to the 2016 LeftPad incident. LeftPad was literally an 11-line string padding package. When the author pulled it over a naming dispute, it instantly broke thousands of global builds, including massive projects like React and Babel. Seriously, if the functionality is just a few lines of code, just write it yourself. Every single dependency is a maintenance burden and a security risk. Before adding any library, you've got to run through a rapid-fire checklist.
Check the commit dates and release frequency. If it hasn't been updated in 2 years, that's a huge red flag. Look at the community on GitHub. What are the issue response times like? Assess the quality of the tests and the documentation. Does the project even have a security policy? And crucially, do not rely on popularity alone. Download counts can be so easily gamed by bots.
Section 5. Building a defense strategy. An SBOM, or Software Bill of Materials, is absolutely vital here. Think of it as the nutrition label for your code. It tells you and your customers exactly what is hiding in your supply chain. It's actually so critical that it was mandated for U.S. federal software by a 2021 executive order. Without an SBOM, when a massive new vulnerability drops, you have no quick way to know if your product is actually affected. The two main formats you're going to encounter for this are Cyclone DX, which was created by OWASP, and SPDX, created by the Linux Foundation. Now, the really great news here is that you do not have to write these by hand. Both of these structured inventory formats can be automatically generated by most modern software composition analysis tools. That gives you instant visibility into your entire nested component hierarchy. To minimize risk dynamically, you absolutely have to automate. Pin your exact versions. Don't just float on latest or use open-ended ranges because an unvetted update could break your system overnight. Try to prefer well-maintained, larger framework libraries over hundreds of tiny, single-purpose micro-libraries. And make sure you run software composition analysis right in your CI pipeline. You can use tools like GitHub's dependency review action to automatically diff dependency changes on pull requests, which outright blocks any merges that try to sneak in high-severity vulnerabilities.
Section 6. The Incident Response Plan.
Look, even with the best defenses, when a dependency gets compromised, panic is not a strategy. You need to immediately follow a solid 5-step response plan. First, identify exactly which applications and versions are affected in production. Second, assess if your specific usage is actually vulnerable to the flaw. Third, mitigate. Apply the patch, remove the package entirely, or isolate the system. Fourth, communicate to stakeholders and notify users if data was at risk. And fifth, conduct a postmortem. Ask why it wasn't caught earlier and use that info to improve your automated scanning. The biggest thing you should take away from this explainer is that dependency management is absolutely not a periodic cleanup task you just do once a quarter. It has to be a continuous review process, hardwired into your CI pipeline and applied to every single line of code you or your team writes. Security is a continuous practice, not a destination. Ultimately, every single library you add is a risk decision. So I want you to let this final thought guide your architecture moving forward. The most secure dependency is the one you don't have. Think about your current code base right now. What single unnecessary dependency can you completely remove from your project today?